we are starting a new unit. It's exponents. We're going to start by talking about the properties of exponents. So you probably know a lot of these properties, but I'm going to go through and list them all, and we'll prove a few of them. So the first one is a to the x times a to the y is equal to a to the x plus y. So the base has to be the same. And if we're multiplying, then we can add the exponents. Now we can say the same thing for division. I'm numbering these, but again, it's just so that it's a little bit easier for us to refer to later on. It's not that there's any order to these. So if we're dividing and we have the same base, then not surprisingly, we can subtract the exponents. And then exponents, we already talked about the fact that they can distribute into parentheses, but they can only distribute into parentheses if inside the parentheses we're multiplying. So this is a times b, so we can distribute the exponent and it becomes a to the x times b to the x. And again, this holds true if we're dividing. So if we have a divided by b, and we're raising that to the x power, then we could say that this is a to the x power over b to the x power. Then we also have anything to the 0 power is 1. If something is being raised to a negative power, then we can make that power positive by putting the a to the x in the denominator. If you raise a power to a power, so if you have a to the x and you're raising that to the y, then you multiply the powers. And that's what we're going to do for now. There are a couple of more with radicals, but we'll take care of that later. Okay, so let's take just some of these rules and prove them. We're not going to go through every one, but I want you to just get an idea as to why things distribute, why we, in this rule number 1, we can actually add the exponents, so that you're understanding why these rules exist and that they're not just coming out of nowhere, kind of like that quadratic formula that we proved. Okay, so let's take the first one. Let's prove this first rule, that a to the x times a to the y is equal to a to the x plus y. So what we're going to do to prove this is we're just going to expand everything, okay? So by definition, a to the x is equal to a times and I'm going to put a dot, dot, dot here. We don't know how many a's there are because this is being raised to the x power. So what we're going to do is we're going to put a dot, dot, dot. That just indicates that there are more a's in between. And we're just going to say that this is occurring x times. And then we can do the same thing for a to the y. So a to the y is a times a, and the same thing. We don't know how many a's there are. So we're just going to say y times here. Okay. So now that we've expanded each of these, we're going to multiply them. And the idea here is that we're going to make the left side equal the right side. Okay, so we're starting on the left and then we'll move on to the right. So a to the x times a to the y is just what we have here times what we have here. So we have our A times A. Again, we're not sure how many there are, so we're just going to say that this is happening X times. And then we're multiplying by A times A. Again, we don't know how many there are, so we just multiply it. We just put that dot, dot, dot in there. And this is Y times. Okay. So each of these, we could put a reason. So for each of these, we're going to put definition of exponents. Because this is what exponents is. It's just this repeated multiplication here. Okay, and that's true for both of these. And then over here, we're actually multiplying. And when we multiply x times, and then we multiply y times, then when we put it together, we have x plus y. So we have xa's, we have y's, so now we have x plus y of them. Okay. Now what we're going to do is, so this is our left side. Let's put that in this nice blue here. This is the left side. Okay, now we're going to do the right side. And if we had a lot of room on this paper, then we might actually put this stuff on the left and then what we're about to do on the right, but we don't have that much room. So we have A to the x plus y now. So a to the x plus y, by definition of exponents, is a times a. And again, we don't know how many a's there are, so we're going to put a dot, dot, dot. And this time, all we know is that this is x plus y times. And once again, this is just because that's what the definition of exponents is. So notice we're putting reasons in here, just so that when people look at our work, they can follow along and know where we're getting this information from. And this is the right side. So now what we have is the left side is equal to the right side. A to the x times a to the y is equal to the a to the x plus y. They're equal to the same thing, okay? If they're both equal to the same thing, then they're equal. So we can make that conclusion. So what we do is we use something called a therefore. So these three dots mean therefore. And we do this at the end of every proof. What we're doing is we're saying, see, we're going to put in this last statement and say, okay, our last statement is our proof. It's saying that the left side is equal to the right side. Again, this is just to be clear. So a to the x times a to the y is equal to a to the x plus y. And our reason here is that they are both equal to the same thing. Therefore, they're equal to each other. Okay, this actually has a name. It's called the transitive property. So you don't always have to write out this whole thing. You would just say transitive property. Okay. And when we're done with a proof, what we can do is we write something called QED. So this is a Latin. I don't even remember what it stands for. But you'll see this at the end of every math proof. And essentially what it means is, we did it, we're done. So in Latin, that's what it is. It's saying, we did it, we finished. And it's another way to indicate to people that, okay, this is the end of your proof. So you have your therefore statement here, therefore a to the x times a to the y equals a to the x plus y, but then this is like your celebratory message. Okay, let's do another one. Let's do the distribution one. So another proof. This time we're going to do ab to the x is equal to a to the x b to the x. Okay. So this is our distributive property for exponents. And we're going to do the same thing. Okay, we're going to make the left side equal to the right side. So we're going to start with ab to the x. So ab to the x is ab times AB, and we just keep going. And we really don't know how many ABs there are, so we're just going to say that this happens X times. Okay. And our reason here is the same as before. It's just definition of exponents. So now we can actually rearrange this. So we can use, this is all multiplication. This is a times b times a times b times a times b and so forth. So we can rearrange this and we can say ab to the x is really a times a and so forth times a, and then times b times b times b. There are x of these, and there are x of these. All we did is rearrange it, bringing all the a's to the front and moving all the b's to the back. And we're allowed to do that because multiplication is commutative. Okay, commutative property says the order doesn't matter. So A times B is equal to B times A. Okay, so AB times AB is the same thing as AA, BB. There's no difference. We can change our order around however we want. Okay. Okay, so we did the left side. So we can mark that off. This I usually wouldn't put in a proof. Again, it's just because we don't have a lot of room, so I can't put the left side on the left and the right side on the right. So we're just indicating the difference. Now we can expand the right side. So the right side says a to the x times b to the x. And we know, using the definition of exponents, that this is a times a times a, x times. And then times b times b times b, also x times. Okay. And that's just definition of exponents. So now the left side is the same as the right side. We showed that they're exactly the same. So this part here is the right side. So now we can go back to our therefore statement. Therefore, a b to the x is equal to a to the x times b to the x. And this is the transitive property. They're both equal to the same thing, therefore they're equal. Okay, transitive property is essentially saying C equals D and K equals D. So C is equal to K, if that makes it easier for somebody to see. Okay, it's just that two things are equal to the same thing, therefore they're equal. And then because we're done with our proof, we can just write QED. Let's do one more, just so that you have an extra one in there. Let's do a proof of that seventh rule. So this is a to the x to the y is equal to a to the x y. Notice that these proofs aren't particularly long, okay? All they are is just using the definition of exponents. So a to the x is equal to a times a. I'm going to put in the reasons at the end. I'm just going to say them now. So this is happening x times. And then if we take a to the x to the y, so we could break this up into two steps. We could say that this is a to the x times a to the x. We're going to put our dot 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 here because we don't know what y is. Times a to the x. And this is happening y times. So then we can break this up even more. So this is equal to every a to the x is a times a And then we're going to put in our dot, dot, dot. So each of these is happening x times. All of these are just definition of exponents. So far, that's the reason for everything. And then this whole thing is happening y times. So here's what we know. We know that this is equal to A happening x times y times. And the reason that we know that is the definition of multiplication. We have x things, so this is x plus another x plus another x plus another x, and that's happening y times. So a short way of writing x plus x plus x plus x y times is just x times y. That's where the x times y came from. Imagine that there were 3 of these, and then we had 3 plus another 3 plus another 3. A short way of doing that is 3 times 3. If there were 4 of these, then there would be 4 plus another 4 plus another 4. So we would have 4 3 times, or 4 times 3. So that's what's happening here. Okay, this is just the definition of multiplication. And now we did the left side, so we can then do the right side. I'm going to put the right side up here, just so that we don't have to go on to another page. So we have A times A, and this is once again definition of exponents. And we already know that this is x times y times. So now we have the left side equal to the right side. So we could put in our therefore statement. So therefore, a to the x to the y is a to the x y. And we just write in our q ed. Okay. So let's just go back through this one more time and do all of our reasons. Okay. So this first one is definition of exponents. A to the x is just a times a times a x times. Okay, definition of exponents. This one is also definition of exponents. We're rewriting a to the x y times because it's being raised to the power of 1. Okay. This one is just definition of multiplication. Well, this one is not really a reason. All we did is we just expanded. Okay, we expanded the first and the second. This one is definition of multiplication. All we did here is just a substitution. So instead of writing a to the x, we wrote a times a times a. We essentially, instead of writing this, we put it in as this. Okay, so we did a substitution. And then our last thing was because of the transitive property. They're both equal to the same thing, therefore they're equal. That was the right side. The left side, this was because of definition of exponents. So this whole section here This was your left side. And this small section here was your right side. So our right side is equal to our left side. Okay. Same thing, right side equals left side, therefore they're equal, transitive property. You can prove all of these other rules in a very similar way. So you can prove, let's go back. It's not. You can prove rules 2 and 4 in the same way. Okay, I want to prove 5 and 6. I want to prove that anything raised to the 0 power is equal to 1. So we're going to prove a to the 0 is equal to 1. I should change colors. Okay, so this is not necessarily quite as intuitive. So what we're going to do is we're actually going to use this property here, this first property. We're going to use this property, that a to the x times a to the y equals a to the x plus y. So if we say a to the x times a to the 0 is equal to a to the x plus 0, then this is equal to a to the x. So now we're going to take out this middle piece just to see it a little bit more clearly. So we're not changing anything. This is the reason. Okay, we're using this rule. And we're just saying a to the y is equal to 0. We're saying let y equal 0. The reason why we're saying let y equal 0 is because this is what we're trying to prove. We're trying to prove that a to the 0 is equal to 1. So we're just going to plug in a to the 0 and see what happens. And we can do that. We can always just, as long as we're not breaking any rules, we can do whatever we want. And if it works, it works. So we're replacing y with 0 and we're seeing, okay, so what happens? So a to the x times a to the 0, we can add the exponents. So a to the x times a to the 0 is equal to a to the x. And that actually means that a to the 0 has to equal 1. We can put a therefore here. So we're already done. And the reason that we're done is that anything times 1 is equal to itself. This is the identity property of addition. So we're done. So we can write a QED. But the reason that we're going to put in is the identity property of addition. Anything times 1 is equal to itself. Sorry, identity property of multiplication. And we're going to use the same concept to prove the last one. A to the negative x is equal to 1 over a to the x. Okay, same concept. We're going to use this initial property that we see here, a to the x times a to the y equals a to the x plus y. And this time we're trying to show something about a to the negative x. So instead of saying y equals 0, we're going to say y equals negative x. And we can do whatever we want, as long as we're not breaking any rules. And we're not breaking any rules here. So a to the x times a to the negative x is equal to the a to the 0. And we already showed that a to the 0 equals 1. So we can use that. So let's take out this middleman, okay, and just write this. This is an x, by the way. So a to the x times a to the negative x is equal to 1. And we can actually say now a to the negative x is equal to 1 over a to the x. We're ready to say that. And we used identity property of multiplication up here. We are going to use the inverse property of multiplication down here. And what the inverse property says is anytime that you multiply something by its reciprocal, it's equal to 1. So this is the inverse property of multiplication. So anything times its reciprocal is equal to 1. So for example, 3 times 1/3 equals 1. 6 times 1/6 equals 1. That's what the inverse property of multiplication says.